Oh, yeah. Now that this is all good, I'm gonna talk about the brute force solution. Anyone has any ideas for the brute force solution? Just asking. No one?
Yeah,
It
you
doesn't.
just
It
you
doesn't have
just
to be.
sort it.
Yeah, you just sort it and then you print the element
Yeah.
at the index that's given over here. Yeah, exactly. That's the brute force solution. So, what would be the time complexity of that solution? It would be O of n log n worst case per query. So, in total, if there are q queries, it would be this. Oh, wait, why did I use uppercase Q here? It should be. So that's nq log n. That's pretty bad. That's not what I promised, right? I promised n plus q log n, but we're just getting started, so don't worry. Now, what I want you to have in mind, basically, we kind of have an advantage here. Why? Because we already know what we're going for. We somehow want to get this to O of n plus q log n. I don't know how we're going to do it, but we want to somehow do this, right? So we already know that there's going to be a log factor involved. We know it can't be due to sorting, because if it was due to sorting, well, it can be due to sorting as well, but if it was due to sorting in the way we are doing it right now, it would obviously just be n log n per query, right? But we know that there's a log n involved. So what does that really suggest to us? There's like three things I can think of that would involve log n. Number one is like some kind of bitwise tricks. Number two is divide and conquer, and number three is binary search. I don't think there's like really anything else that would make the time complexity have a log n in it. Does that make sense? Okay, I'm just going to assume that you guys agree with the sentiment. Uh, Now, if you guys have studied segment trees before, you will have seen that the way segment trees work. I'll just draw like a small thing over here. You have like this big array that you divide into smaller ranges, right? And you keep doing this by dividing it into half each and every time. So this is going to represent the entire array. This is going to be the half of the array where the elements. Sorry, it's going to be this half of the array. This is going to be this half of the array, right? This is just like your regular segment tree. Now, what I'm going to say next might come as a shock to people, but in Wavelet trees, you do divide and conquer. Of course, it's like a tree, right? But you do divide and conquer on the actual values that are stored in the array, not on the indices. Okay, so does anyone have any idea what I could possibly mean by this? I want you guys to, because you can be wrong, that's fine, because this is probably going to be a new concept for a lot of people, but I just want to know, what do you think I mean when I say I'm doing divide and conquer on the values instead of. Oh, there is. Oh, sorry, I didn't see chat. There is another way to solve this, of course, and that way is using this thing called persistent segment trees. But the thing is, I like the Wavelet tree solution more, and also it uses less memory. So, in my opinion, it's just objectively better. Okay. But anyway, coming back to my question, what do you think? What do you guys think I mean by dividing and conquering by value? Just any ideas would be fine. You can type it in chat as well. Secretary type data structure on the values of the array. Yeah, that's kind of going in the right direction. That's pretty close actually. Maintain two pointers. Okay. That was a nice try, but we are actually going to be doing a segment tree type thing, so it's fine. You'll see what I mean when we do it. This idea is actually really cool. Anyone else have any ideas? Want to think about what we could potentially be doing over here? Because, like I said, this is like a very interesting and novel idea. You can have a count of elements for each value and then do a binary search. you're actually not very far off with that as well. It's like you're getting the root ideas we're going to be using, but when we tie it together, it's going to be pretty cool. Okay, so uh, now I'll explain. I won't explain the full thing, but I'll give you guys some hints on how this is going to look. So, let me pull up my thing. Let's say I simplified the problem a bit, just for our understanding. I'm just going to draw another array, and I don't know, I'll put random values in it, like 1, 7, 6, 2, 5, 3, and 6. I don't know. Okay. Now, I'm going to ask a new question. In this question, what I'm going to say is that I have an array, and I have queries of the form just the value k. So just queries are of the form k, and my task is to print the kth element that would have occurred if this the kth smallest element that would occur in this array. Do you guys understand what the question is? The updated, slightly easier question. So I feel like most people, when I say this question, their reaction is gonna be, okay, dude, what? Like you can just sort the array and print the kth element. What's the big deal about this, right? And you would actually be right. That you can definitely do that. But the reason I'm going through this question is because I want to think about another way we can potentially solve this question. Something related to binary search. So okay, so first of all, did everyone is everyone clear with the question? And the yeah, sort before queries, exactly. That's of course a valid solution. So that's good. You understood the question. Uh, you guys could see my iPad, right? When I was presenting, I stopped presenting now just because I wanted to see chat. Okay, yeah, perfect. I don't have two monitors, so unfortunately I have to do stuff like this. How can you use binary search without sort? Oh, you haven't even begun to see how many places binary search can be used. Also, what we are going to be doing here is going to be kind of an implicit sort. So, okay. Okay, good. So everyone understood the question, right? I'm assuming. If anyone didn't, please ask. It's like really okay. You want to think about how to solve this with binary search. See, the thing is, you already have the optimal solution at work, so that's the reason I would probably like not want to do this because you can't really get better than this. The solution I'm going to describe is objectively worse in this case. But it will like show you. Oh, we can also think of it this way, you know. So do you still want the 5 minutes, or I would rather that I just explained it because okay, cool. So now my objectively worse solution, but still kind of interesting, is what I'm going to say is okay. What's the minimum element in this array? The minimum element is 1. What's the maximum element in the array? It's 7. Okay. So I know that all of the elements in this array are in the range of 1 to 7. So now what I'm going to do is I'm going to say, let me look at the midpoint of this value range. What's the midpoint of 1 and 7 is 4, right? So let's divide this into 1 to 4 and 5 to 7. Okay. Now what I'm going to say is I have this original array. Can I make two arrays out of this such that everything on the left is between 1 to 4 and everything on the right is between 5 to 7? So I'll just show you how this would look like. Um, I'll rewrite the original array here just because we're kind of running out of space. Oops. So like I said, the midpoint is 4, so we're going to divide this into two parts, one which is less than or equal to 4 and one which is greater than 4. So what we're going to do is we're going to pick up elements. So we're going to pick this element up because it's less than 4. 7 we're going to skip because it's greater than 4. 6 we're going to skip. 2 we're going to pick that up. So we're going to write 2 here. 5 we're going to skip. 3 we're going to write here. And 6 we're going to skip. So actually I realized I drew this a little too big because most of the elements are less than 4. So I should probably fix that. So we just have 1, 2 and 3. Okay. And then the remaining elements would be greater than or equal to 4. So the first step of the solution is you partition the array into two arrays where the left half is the elements less than or equal to the middle value of the value range of the array, and the right half is the ones greater than or equal to this. You'd say, okay, fine, I guess you can definitely do that. Then what's next, you know? I'll do the same thing again. So what do I have over here? I have values in the range from 1 to 3, right? What's the midpoint of 1 to 3? That's just 2. So I'm going to have values here less than or equal to 2, here greater than 2. Okay, I have this again. So let's just do that again. So this is 1 and this is 2. Again, over here we have values from the range of 5 to 6. Is that right? No, I feel like, oh sorry, it's 5 to 7, right? So 5 plus 7 is 12, 12 by 2 is 6. Again, we're just gonna pick up the elements less than or equal to 6. So that's this 6 over here, 5 and 6. The 7 is going to get ignored. And then greater than 6 is just going to be the 7. Then we're going to do the same thing here. Okay. And after all of that work, we have come up with this really complicated tree-looking structure. Okay. So now how do we use this to even answer our query? Our query was we want to find the kth element, and we built this super complicated thing, right? Okay. So we are over here. We can say, okay, is our kth element less than or equal to 4? Suppose this was true, then we know that k would be between 0, 1, and 2. In index wise, actually, you know what? Just to make this more clear, I'm just gonna label the indices of the array here. Now, please try to understand this because this is like where the real meat of the algorithm happens. I'm saying if k is equal to 2, that means I want to access the element at index 2. Okay, or actually, let's not do that. Let's do k is equal to 3, meaning I want to access the value at 3. Okay, like the third value. Let's say the array is this, so I would ideally have wanted to access the element 3. Okay, basically, what I'm saying is now we're going to look at how many numbers are there that are less than or equal to 4. If there are more than or equal to k values that are less than or equal to 4, we know that the kth value is actually going to be less than or equal to 4. Otherwise, we know that the kth value is going to be greater than 4. So I'll just repeat because I'm sure that was confusing as hell to anyone who doesn't know the concept. Um, or who hasn't seen this before. You know, this is actually kind of the same idea used for persistent segment trees as well. So I'll just repeat again. You have an array. You want to find the kth value in the range without sorting the array. So what we're going to do is we're going to build this super complicated looking tree structure, okay, where the left will basically just extract all of the elements that are less than or equal to 4 in this case because 4 is equal to 1 plus 7 by 2, and the right half will be greater than the midpoint. I do this continuously until my value range collapses to where the elements are equal. Okay, wait, sorry, I just need to let this person in. Yeah, I think, see, the thing is with CP, in respect to what Hardeen said, sorry, not Hardeen, in respect to what Ludwig said, the entire idea of divide and conquer, it's kind of like the same thing wherever you use it. Just kind of why I like this idea a lot, actually. Because once you learn it, you'll find that you can apply it to so many data structures that do like slightly different things. This is correct, by the way. This is kind of what we are doing here, except we're not maintaining a secretary. But you can kind of see how what we're doing here is basically just a binary search on value range. Okay, so how many people here have done a binary search on a value range before? Like questions where you have to binary search on the answer using a predicate function. How many people here have not done it? Actually, I should ask that because that's kind of more important, right? Because I'll need to explain it then. Like seriously, if you haven't done it, I am anyway gonna explain it, but I wanna like know just so I can like make sure that you guys like understand later. No, not just binary search on answer. Like where you need to call some function to check if this is applicable or not. Okay, okay, that's good. So it seems like most people. Can I summarize? Okay. So when did you leave? Like, from what part do you want me to summarize? Okay, I'll just do a quick summary. Uh, because I think it will help other people too. Because just going through what we're doing again. Yeah, just give me a second. Let me. Yeah. So we started at kth order statistics. We came up with an NQ login algorithm. Then we were like, this is not what I told you I would give you. I said I would give you n plus q log n. Then we noticed there's a log n in the algorithm's time complexity. So we're like, this must involve some kind of binary search, divide and conquer, or bitwise tricks. Can't be anything else, right? Then I briefly recalled what the structure of a segment tree looks like, which does divide and conquer. Then I went to a simpler problem where I said, okay, instead of finding the smallest element in the range L to R, let's just make the query the entire array. Find the smallest element, find the k smallest element in the entire array. And then, as a lot of people, specifically Advik pointed out, you can just sort the array in the beginning and answer queries later, which of course that's a valid solution. But then I was like, okay, that's too simple. I wanna complicate things. So then I built this entire tree, and now I'm explaining an alternative solution to solve the same problem. So that's the summary. I'm going to explain this part again. Did you get what the summary is? Vasav? Okay, perfect, perfect. That's great. Okay. So now I'll explain this again. Basically, what we are doing here, we start with the original array. We find the smallest value in the array and the biggest value in the array. So in this case, that's 1 and 7. We find 1 plus 7 by 2, that's the midpoint. We put all elements less than or equal to 4 in the left half, taking them in the same order as they appear in the array without changing their relative order, right? Take all of the remaining elements that's greater than 4, you put them in the right half over here. You do the exact same thing all the way down until your leaf nodes just consist of a single value, not a single, single value range, not necessarily just a single value. It can be multiple, like two values, but they both have to be equal to each other. Okay. Now what I said is that we want to find the third smallest element or the kth smallest element in general in this range, right? So what I'm going to say is I'm going to start at this, and I'm going to initially know that hey, the kth smallest element has to be part of the array, right? That's pretty obvious, right? The kth smallest element obviously has to be part of the array. Now we're going to say, since it's part of the array, we know it's definitely between 1 and 7 because the minimum element in the array is 1 and the maximum element in the array is 7. Okay, great. Now I want to somehow divide this range of values we know it's potentially between in half. So what I'm saying is, okay, is there any easy way we can check if it's between 1 to 4? Like, if we can we be sure that it's between 1 to 4? Or otherwise, it's between 5 to 7 because we know it's definitely between the bigger range. So if it's not between 1 to 4, it's definitely between 5 to 7. Is this kind of making sense to you guys? I'll just pause for like, I don't know, like 5-10 seconds just to let that sink in. Okay. So what I said is, how do we check if we now that we know it's between 1 to 7, how do we check is it between 1 to 4 or not? The answer is you simply count how many elements in the array are less than or equal to 4. And it's these elements, right? It's three elements are less than or equal to 4. And we know that k is also equal to 3. So if we know k is equal to 3 and we know three elements are less than or equal to 4, then we know that the element we're looking for is going to be less than or equal to 4 as well. Now we know it's between 1 to 4. So it's going to be here. Does this make sense to people? Just please repeat. Okay, I will repeat once more, just so it's extra, like absolutely clear. So I was saying, you have an array. This is the original array, and I want to find the third smallest element in this array. Okay, what I'm going to do is initially I know that the third smallest element is between 1 to 7. Why do we know this? Because the array's minimum element is 1 and the maximum element is 7. That's the first part. The second part is now I want to somehow find out is the we're going to take the midpoint of the value range, not of the index range. So this is like kind of divide and conquer on the value. We're going to say, is it less than or equal to 4 or is it greater than 4? Now, how do we check whether the value we're searching for is less than or equal to 4? Well, we have to count the number of elements in the array that are less than or equal to 4 themselves. How do we do this? Well, we know these are the elements, right? We just go to the left tree and we count those elements. That's how we do that. Now, the number of elements less than or equal to 4 is 3, and k is also equal to 3. That means that the third smallest element has to be over here. That's why the third smallest element, we have shrunk the range from 1 to 7 down to 1 to 4. So do you essentially see how this is like doing binary search on the value? We can actually, there's nothing stopping us from repeating the exact same process for this as well. Like, I can show you how to do that because it's not that hard, right? So we're now going to do the same thing. We're going to check, okay, now we know it's less than or equal to 4. Is it less than or equal to 2? Let's check. There are only two elements that are less than or equal to 2. But we want the third element. So it definitely can't be less than or equal to 2. It has to be to the right, right? I'll just repeat that once more. K is equal to 3. And we want the third element. That's what that means. Now we're going to check, is the element we want less than or equal to 2? The thing I'm saying is it can't be less than or equal to 2 because there are only two elements that are less than or equal to 2 and we want the third element. So by that logic, we just know that it has to be in the right. Does that make sense? Do you see how this is just binary search? It's just glorified binary search. Yes, yes, it is exactly just binary search on the tree. Divide and conquer on the range of values. Yeah, exactly. Okay, so this is clear, right? Like, actually, the thing is, if you understood this, surprisingly, this is like I think 50% of the concept behind Wavelet trees. But the issue is that most people don't understand this that well because I guess they just don't go through it and sit down and I don't know. Maybe that's why Wavelet trees are perceived as hard, or I don't really know what it is, but yeah. I'll just give you guys 1 or 2 minutes to think about this. Okay. So now, uh, there's a word for what we're doing actually. This thing where I said, oh, you have a single array. You take all of the elements less than or equal to 4 and you make them into an array. You take all the elements greater than 4 and you make them into an array. I don't know how many of you guys have heard of this, but there's this STL algorithm um, called SE partition. How many people have heard of this? Okay, basically, if you haven't heard of it, it does exactly this. You give it an array.begin and an array.end, and it partitions all of the elements less than or equal to x, and you give it an x. It partitions all the elements less than or equal to x to the left half of the array, partitions all of the elements greater than or equal to x to the right half, and it returns a pointer to this point. So the beginning of the right half, it returns that. Actually, I just want to check if I can see the algorithm window. Does it say? Move elements for which a predicate is true to the beginning of a sequence. So in this case, the predicate is going to be the element is less than or equal to x. And it will move them all to the beginning of the sequence. So this is an algorithm. It does what we expect, uh, except not really, because this doesn't have any guarantees to produce a relative order. Basically, what this means is if I had something like 3, 2, uh, 10, 9, and I wanted to partition this with x is equal to 5, do you see how the answers 3, 2, and 10, 9, this is also correct, right? But
Sorry for interruption, but could you please make the font a little bit bigger in
yeah,
VS Code?
um, for sure, for sure. Okay, I'll just full screen this for now as well, maybe, just so you guys can. Oh, oops, I did not mean to do that. Okay, is this better? You want me to make it bigger? Because I can.
Yes, it's better, but maybe a slightly bigger would be better. Yeah, that's fine. Perfect.
Okay, cool, cool. So, like I was saying, we partition with x equals 5. You can get this. This is what we were doing actually on the iPad, right? But you see how you can also get this, and it's a completely correct answer as well. Like, I have done what they've asked, right? I've partitioned it into two arrays where the left half is less than or equal to x, and the right half is greater than or equal to x. So, hey, well, like, why are you complaining, right? And in fact, this could have also been the correct answer. Um, Basically, I'm pretty sure you got the point. Is that the relative order between the elements. So like the fact that 3 comes before 2 here, that's not preserved, or it doesn't necessarily have to be preserved by STD partition. That's why we have this other function called stable partition. Performs the same function as partition with the additional guarantee that the relative ordering of elements is preserved. So if any two elements x and y in the range, first to last, such that the predicates are equal, they will have the same relative ordering. So this on the other hand, this is good, right? This is exactly what we want, stable partition. This is what we have been doing, like exactly what we've been doing on the iPad as well. So in this case, if you use this, this would be the only right answer. Now one more thing, I'll just explain this here actually because I don't know. Or wait, should I explain this here? Should I explain this here? I don't know. You know what? I'll explain it on the iPad. 3, 2, 10, 9. Okay. Like I was saying, let's say we had a range in this original array, okay? Some kind of range. Now, what is going to happen to the left array? The left array, we'll just say less than or equal to 5. We're just going to say this is greater than 5. What is this left array going to be? It's going to be just the original array, but the 10 is like cancelled out. It's like gone, right? And even the 9 is gone. Actually, wait, maybe 3 to 10 9 isn't that great of an example. I think it would be better if I just changed. Okay, yeah. So what is less than or equal to 5 over here do? I'm going to write 3. I'm not going to write 10. It's kind of like the space is gone. I'm going to write 2 again, and I'm not going to write 9. And then what about the right half? The right half is like the same thing, but all of the elements that are gone in this case won't be gone, right? So you have 10 and 9 here, and these two are just not there. So my point is with all of this is that if I have any contiguous range in the original array, let's say I have 10 to 9, it's going to be a contiguous range in every other subsequent array as well, right? I mean, these elements are just going to be deleted, but it's still going to be a contiguous range. Do you get what I mean? If Y created a tree, why would we need to create it again? Sorry, what do you mean by that? Yeah, I'll repeat. Just I just wanna. Is it going to repeat it SE stable partition per query? No, this is going to be the construction. The query is another thing entirely. The time complexity of stable partition is O of n, I'm pretty sure, because you can code it in O of n, right? There is going to be SE stable partition per layer of the construction, not per query. I'm gonna repeat what I said just because someone asked me to. Uh, just let me. Yeah, so I'm saying let's just go back up over here. What was our original intent over here? Or actually, wait, I did not go over intent yet. So it's fine. I'll just. Basically, what I'm saying is you have this array. If you take any range in this array, like any range of like a contiguous segment of values, like I'll take this range. If I'm going to go to the children array, it's like children arrays, like this array and this array, I'm saying it's guaranteed that I'm going to have a range in them as well. Like I won't have like for example this and then directly like this or something like that or like sorry directly like let's say there was like a I don't know 4 over here. I wouldn't have this. This is not possible. That's what I'm saying. And why is it not possible? Because this over here would correspond to some range over here, but just that these elements are missing. But just because these elements are missing, you can just like imagine removing them and then you'll still have a range. That's what I was saying. Okay, so not a subset. I mean, subset is like a weaker condition. Specifically, its range. That's the important thing. Oh yeah, if you change the relative order, it won't be a range. Yeah, exactly. Then there's no guarantee there'll be a range. But if you do stable partition, then it will be a range. See, it's not necessarily L, M, and MR, but it's going to be some range. That's all I'm saying. We don't know what the range is yet. I'm just saying that it is a range. Now, uh, need to go back to this and share my screen again. Now, I want to ask you guys. We did this question, right? Where we wanted to find k is equal to 3 in the entire array. My question is, what is the difference between these questions? Maybe, I don't know, like we can say this is question number 1. And what's the difference between this original question we had, say question number 2? Like, what really is the difference? The only thing that changes is over here, we don't consider the entire array. Now we just have to specifically consider a range, right? That's it. That's the only thing that changes between these two questions. And you might be like, oh, right, that's the only change, but this change kind of makes everything stupid. Right, like I was saying, oh, you're saying this is the only change, but this change is kind of like, it's such a big change, it makes everything harder. But does it really make everything harder, or does it not? That's my question. Now, what were we doing before? We were counting how many elements are less than or equal to x, right? And how many elements are greater than x. And depending on if we had enough elements less than or equal to x, we would go to the left. If we didn't have enough elements, then we'd go to the right. This was what we were doing before, right? So now I'm saying, what if? What if we only counted the elements less than or equal to x in this range in particular? We can do that, right? I mean, I haven't told you yet how we would do that, but let's say we did do that somehow. And then depending on whether there are enough elements just in that range, we go to the left. Depending on whether there are not enough elements, we go to the right. Then when we go to the children, like I said, we're going to have a range again, so that's not an issue, right? In the beginning, maybe you would have an objection that, after doing stable partition, this is such a complex operation. How do we know that we're going to have a range again, that we can repeat this recursively? But you can. That's the thing. Why can you repeat it recursively? Because you have a range again. And now this question is the exact same thing. It's like, in this array, between these indices, how many values are less than or equal to x? If there are enough, you go to the left. If there are not enough, you go to the right. Do you guys kind of understand what the idea is? Do you guys kind of see how what wavelet trees do make sense? Because this is literally a wavelet tree. What I just described right now, it's a wavelet tree. So it's actually what I described. It's like really similar to what persistent segment trees do as well, except they allow persistence and wavelet trees don't. The range is not index range. This is very important. The range is the value range. You're binary searching on what possible value it can be. Oh wait, sorry, I confused things. I am assuming you were asking the question about this. Yeah, of course. I'm really sorry. The range you're binary searching on is the value range. The range I was talking about right now is the index range. Yeah, you're right. I'm sorry. Uh, so you're basically right, is what I want. What I mean. Yeah, for sure, for sure. I know this will probably be confusing. The good thing is that once you understand it, it'll be like really, you'll be like, holy shit, like what, you can do this. You know what? Instead of that, why don't I just explain with an example? Let's say in this array, um, let's just take this exact same thing, okay? But now we were first saying we want to find the third element in this entire thing, right? Let's not do that. Let's, I don't know, find the third element in this range over here. Uh, so this is 0, 1, 2, 3, 4, 5, 6. Let's find the first element, or sorry, third element in the blue range, okay? What we're going to do is we're going to follow the exact same logic. We're going to count the number of elements less than or equal to 4. Okay, how many elements are less than or equal to 4? There's this, there's this, there's this. Yeah, that's pretty much it, right? But wait a minute. Do we consider this? I put a tick mark over here, but do we consider this element? Well, no, we don't, right? Because our range is only 1 to 5. So if we consider this element, we would be saying that, hey, there are three elements less than or equal to 4, but that's not actually true because in the range we care about, there's only two elements less than or equal to 4. So basically, we don't consider this. This is a cross, right? This is not considered. So there are two elements less than or equal to 4, and k is equal to 3. Does that mean that the value is less than or equal to 4 or greater than 4? It means that the value is greater than 4 and less than or equal to 7 currently. Now we do the exact same thing. So now we know it's between 5 and 7. I will. I will go down here. Now we know it's between 5 and 7. But we need to still consider our original range. Now this is going to be a good example of the range idea I said before as well. Look here, this is a contiguous range. And now what is the contiguous range that corresponds to this? I have 7, 6, and 5. It's this range. Do you see how the child range was also a contiguous range? This was what I'm saying. It's like an action over here. So I go down to the right child and it's a range as well. And now basically my question is only considering this range, because that's what the original question was, right? Now basically what I've just done is I've cancelled out these elements. You can think of it like that. Because we know they're not relevant. So now we're only left with these elements. The question is, what is the third element? Or sorry, not the third element. Since we cancelled out two elements, now we have to get the first element, right? Because we just got rid of these two elements which we knew are smaller. So now it's like 3 minus 2 is equal to 1. So now we need to find, now this is like solving for k equals 1, right? Because if I was saying the third element in this array, it would like, what would our answer actually be? It would be 2, 3, and 5, right? This is equivalent to saying the first element in this array, which is 5. The reason is because I've like basically cancelled out two smaller elements smaller than 5. Anyways, so now you see how you can just do the exact same thing again. Okay, fine. Now, what do we need to do? We have our value is, what did I say? It's in between 5 and 7, right? So is it less than or equal to 6 or is it greater than or equal to 6? Okay, let's see. In this blue highlighted part, how many values are less than or equal to 6? Um, well, 7 is not. I don't know why I take that. This is, and I, okay, can I take this? I can't take this. Why? Because it's not in my range, and we only care about the values that are in our range. So how many values do we have? We have two values. And what is k equal to? Now k is equal to 1. So we are like, yes, we have enough values, so we can go here. Right? Now we go here. And now we actually have to make sure we translate our indices again. So like I said, 7 gets cancelled in a way, and you're left with just this range. Again, importantly, it's a range. It's always a range when you go down. That's what makes this entire thing possible. So now we have 6 and 5. Again, we're going to do the same thing. We're going to say, hey, is our value less than or equal to 5? So, actually, how many values are less than or equal to 5? So, that's just this. What is k equal to? K is equal to 1. How many values are less than or equal to 5? 1 values. So, we know that it's on the left. And eventually, when we get down to a range where L is equal to R, so there's only one possible value it can be. We just know it's that value and we return 5. How to keep track of what's in the range and not? Oh, that's the entire question, isn't it? Don't worry, it's actually not as hard as it looks. Well, firstly, I'm pretty sure if I gave you guys like, I don't know, 5 or 10 minutes, everyone over here would be able to figure out how to do it with binary search. But the issue is that would be O of log square per query, and we want to do log per query, right? But don't worry, I'll show you guys how to do it in log per query as well because it's pretty cool. Let me just see what. How do we know that one is not inside the range while we are in the queries? Okay, basically each and every query is passed in a range that it is valid for. Each query has an array, right? Like I drew the arrays on screen. So you can like in the actual Wavelet tree implementation, it turns out you can afford to actually even store that array. So then you straight up know what's in the range and what's not in the range. Like, do you get what I mean? There's no complication to that. So the function knows. Yes. Let me read the remaining messages. Eliminate the elements in the small array is ordered. Yeah. Well, it's not because it's ordered necessarily, it's just because we know that all of them are smaller than when we move to the right. Take the first element after position I and everything after. I'm not sure what you mean by that. Can you please elaborate? So there's an easier question. Like, I'm sorry, I'm not understanding what you're saying. Otherwise, I would definitely answer. The thing for Hardin is that what you need to realize is that we're, at each and every step we are dividing the value range by two, right? So how many maximum layers can be there? O of log of max value. That's the answer, right? So there are log max values. So let's just call that log CL M. Okay. These are the number of layers. Each layer can obviously only have n elements, right? Worst case n size. So the total amount of space we use is n log m. So it is fine. I hope you understood what I was saying. I can repeat. Yeah, so I'm saying that the maximum, say the maximum value in the array is equal to m. Then at max, you're at each and every step you're dividing and conquering the array such that you're halving its range, right? So that means that there are going to be a log CLM possible ranges, or sorry, possible layers that you form. Like in the original thing, I'll just hold it up here because I don't want to go and present it again. You can see that like this thing is a layer, 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 right? All I'm saying is that there are O of log m possible layers that can form, right? Because you divide it in half at every step. It's the same idea as the time complexity of like binary search. Oh, Harleen, did you understand? For the queries, how do you know that a value is in the range or not? Okay, yeah. So see, I haven't taught that part yet. That's the next thing I'm coming to. Good that you have that question because obviously you needed to solve the problem, right? But I haven't taught that yet. Right now, I just want you to understand how the procedure works, and then I'll tell you how to actually do it. Okay, wait. Assuming we are considering 3471 less than 8, yeah. Order we need to find. We have range L to R. How many of these will be there in that range in the array? We can just do a binary search to find this. Oh, yeah, but this will be log square n, right? Because you're doing a binary search at each layer and there are log many layers. Like you can do it, but then the thing is you can also use ordered sets. Because ordered sets also have, I'm pretty sure, log square and complexity for solving this. If you use small to large merging with them. And objectively, that's a simpler solution. Yeah, ordered sets are pretty cool, I will admit to that. But wavelet trees are cooler because they have a better complexity. So you can't argue with that either, right? I mean that's objectively they're better. Okay, now the question which Harleen asked, how do you know if a value is in the range or not? Now that's the real root of how wavelet trees work, right? So um, let's just go here. I'm gonna write this original array 1762536. 1762536. Oh, just give me a minute, guys. Something's going wrong with the iPad. Okay, wait, what? Okay, so in terms of the app I was using, oh, can I give you a hint on how to do this instead of giving the full solution? You know what? Sure, I can. Why not? Let's do that. So your hint is look at the tree thing I built before, which I was drawing. Look at what I just did, right? Okay, no, wait, but you already know that. So I need to give a bigger hint on relation to how to make it log n. Okay, so your hint is try to prefix some on the predicate. That's all I'll say. Because I think if I say more, I might give away the entire solution. So I'm just gonna say that much. A predicate is that either you're less than or equal to m or greater than m if your range is L to R for your current node. Well, the thing is, you can always coordinate compress, right? If you want to assume that. So sure, you can assume it. Like, there's no reason I would say no to that. So. Okay, so the thing is that app which I was using apparently it has a usage limit and I exceeded it, which is quite sad. But that's fine because I have free form on this, so I can still teach. We're still fine. So I'll give you guys maybe I don't know 1 or 2 more minutes to think about it. Don't worry if you don't get it because, like I said, it's a really new. Okay, the hint was that you need to prefix some on the predicate, and I won't elaborate on this because that's the next thing I'm going to do when I'm saying the solution. Uh, the predicate in this case is that either your value is less than or equal to m or greater than m. It's the thing you run stable partition on, right? Okay, let's say 10. I'll start discussing at 10. Oh, right, you can do that. Yeah, I haven't. So this is my dad's iPad actually. I don't have an iPad of my own, so I haven't really experimented with the features and stuff. So my iPad knowledge is very rudimentary. I know you can write on it. That's pretty much it. Makes sense. And I think there's a chance my dad might get mad at me if I link my Mac or something to his iPad. So I'm just not risking it. It's fine. For every subray that you make, keep a prefix sum for how many elements? Yes, Advik is correct. That's exactly what you do. That's exactly what you do, yeah. So Advik, what does this count? Prefix R. Well, actually, prefix R minus prefix of L minus one. But uh, but that's fine because you're pretty much right in spirit. And if you change your indexing, then that would also be correct. So I'll give you credit for that. That's correct. So in this case, what would prefix R minus prefix L be? Can you explain that as well? It would just be the number of elements less than or equal to m. Yeah. Exactly. And like before what we were doing is we were like saying before what we were doing is we were saying we need to somehow figure this out, right? And now we figure out a way to figure it out. So okay, so now it's 10 p.m. So that means it's officially time for me to explain. Um, Wait just a second. I need to figure out what the array I was using was because I need to use a different note app. Just give me a sec. Um, so 1762536. I'll just write that in chat. Okay. 1762536. Okay. So we're gonna have to swap to this app, but that's fine. So what we're going to do, like Advik said, we know that the minimum value, I'll just write this just for you guys' reference. Minimum value is 1, max value is 7. So so basically we are going to, our predicate is going to be, uh, our predicate is going to be, is the value we care about less than or equal to 1 plus 7 by 2, that's 4. We're going to make this prefix array, uh, where I'm just going to, okay, can I somehow get rid of this? Okay, that's fine. We're gonna call this array some random thing. For now, I'm just gonna call it map left. This is going to be 0 if the element at the index is less than or is greater than 4, and otherwise it's going to be 1. So right now I'll just write the indices here. So the first thing, the first element is less than or equal to 4, so this is going to be 1. The next element is greater than 4, so this is going to be 0. This element is greater than 4, so that's going to be 0. Then this is 1, this is 0, this is 1, and this is 0. The next thing we're going to do is we're going to prefix sum on this array. So, um, holy shit, that was a lot of lag. So you prefix sum, and you get 1, 1, 1, 2, 2, 3, 3. Guys, just give me a second. I feel like my iPad is lagging. I'm not sure why. Let me just close some apps or something just to see if that improves it. Oh, why did I open that? Yes. Okay. Now, let's say I wanted to count the number of elements in total that were less than or equal to 4. This is just gonna be 3, right? It's this number over here that represents the prefix sum of the predicates of all elements being 1 if they're less than or equal to 4 or 0 if they're not. Does that make sense? This is like what we were doing before. But now the extended idea is that let's say I only want to do it in this range, okay? It's going to be 3 minus 1. Minus 1 because now we're excluding this. It's the same prefix sum idea. Prefix of r minus prefix of l minus 1 will give you the number of values in L to R that satisfy the constraint of being less than or equal to 4. So, did you guys understand what Advik's idea was? Well, it's not like Advik's idea. It's the right idea. But did you guys understand this idea? Oh, this was not your idea. Yours was worse. Oh, I see. Okay. Well, this idea, you should learn this because this is a good idea. You know. Okay. I'll just repeat once more. Okay. Wait. Before I repeat, actually, I will just stay in chat and basically, what was I trying to do before? I was just trying to count the number of elements less than or equal to four, right? Yeah. So now, do you see how this is the same thing as saying I'm going to add one for every element that's less than or equal to four? Of course, that's the same exact thing. Now I can also add another condition. I can say, oh, if an element is not less than or equal to 4, I will add 0. Because that, of course, doesn't change anything. Now, I'm saying that I'll make a new array where the element is equal to 1 if the original element is less than or equal to 4, and otherwise it's equal to 0. Okay, that's my new array. Now, this is the same thing that I just described to you. Now, what I'm going to do is I'm going to prefix sum this array. That means I'm going to convert it into a prefix sum array of itself. And I'm going to obtain this other new array. So in our example, the prefix sum array was 1112233. And now, if I want to find out the number of elements less than or equal to 4 in a specified range, L to R, I just do prefix of R minus prefix of L minus 1. And the reason this works is because of how we define our predicate function. Got it? Perfect. Okay. Did everyone else get it too? Okay, I'll explain it once again while presenting my thing. So just so you guys can see the thing as I speak. I don't think it's the I don't think it's the Apple Pencil's being low battery. I think this iPad is just like really laggy. I don't know why though. It's kind of strange because Apple products are supposed to be, like seamless and stuff. So, but whatever, that's fine. So this is my predicate function, is what I was saying. Like I said, I'm going to write every single number that's less than or equal to 4 as 1. So this number is less than or equal to 4, this number, and this number. So as you can see, those are the only ones in the array, everything else is 0. Now I'm going to prefix sum this array. So this is 1, 1, 1, 2, because I added a 1, 2, 3, 3. And now, if I want to find in the entire array how many elements are less than or equal to 4, that's equivalent to saying the sum of all of this, right? If I only wanted to find it in a subarray, let's say I wanted to find it in this subarray, it's the sum of this subarray. But from prefix sums, we already know that the sum of this subarray is equal to the sum of this whole subarray. Oops. I'll use a different color. I'll use yellow. Minus the sum of the yellow elements. So it's blue minus yellow is equal to this blue over here. So that's the idea. So prefix of R minus prefix of L minus 1 will give me the sum of these elements. And what does the sum of these elements mean? The sum of these elements means the number of elements in the range which are less than or equal to 4. So you do this for each predicate at each level. Yeah, exactly. Harleen is right about that. At each and every level you store. Okay, so the thing is it won't. The reason it won't, I'll just explain this again, is at each level, how many elements do you have? You have at max 10 elements. Do you agree with that? Yeah, right? At each level you have n elements. Now the question is how many levels at max can there possibly be? So from segment trees, we log m to be fair, but if you coordinate compress, yes, it would be log m. So what I was just looking for is it's going to be logarithmic with respect to some value that's like going to be bound by like 10 raised to 9 or something. Why are the log m possible layers? Because at each layer, the range you're looking at. Okay, if you don't know what coordinate compression is, that's fine. You can just ignore that part because technically you don't need coordinate compression for it to pass. Okay, I'm happy that you understood now. Although maybe since people don't know what coordinate compression is, maybe it's a good idea to hold a lecture on that as well. Although it's like a really, I don't know if there would be enough content for a lecture. Yeah, maybe I'll just like have a text discussion about that later. I don't know. Yeah, maybe that too. Okay. Uh, Anyway, like Haldeen said, I don't really need to go back to the iPad right now. You can do this for each predicate at each level, and now the only task we have remaining, like we have done majority of the things, right? The only thing that is remaining is to figure out how you remember I said that you have a range and then you go to the left and the right side you still have a range. But I never really went into what that new range is going to be. I just said it will be a range, if you remember. You guys know what I'm referring to, right? Can I get some more confirmations? Because this is also an important part. I can repeat what I said as well, if maybe you guys didn't hear that. So I said, remember before I was explaining that entire range idea, right? I said that, oh, I cancel out these elements, and if I have a range in the main array, the children will also be ranges. I said something like that, right? And now I'm pretty sure conceptually it's clear to people that if I gave them the question and I showed them an array, like you'll be able to figure out what the range is. But I never actually explained how you do it using like C++ or programming. I didn't give an algorithm for it. Or I didn't even formalize how we did it. I just say that it's going to be a range. I formalized that part, maybe. I didn't formalize how you actually obtain the range. That's what I was saying. Right. So, do you guys want time to think about how you can do this as well? Or should I explain it? Okay, I'll repeat the question. Actually, let me just go back to the thing where I explained it on that app, just so you guys can. Um, yeah, so look here. I said that if I have some array, uh, where's my mouse pointer? Yeah, I said if I have some array, like this array, and I'm querying only a range of it, uh, then when I go to the left and the right children, what I'm going to have remaining are also ranges. So this is 3, 10, and 2, right? So what is my corresponding range going to be here? It's going to be this. It's going to be 3 to 2. You can think of this 10 as like kind of being cancelled away. So you're just removing elements from the middle of a range to form that smaller array. But at the end, you're still going to have a range. This range is going to be of size 2. It's from indices 0 to 1. Similarly, if you look to the right, 3, 10, and 2, which range would this correspond to? It could correspond to just this 10 over here. So it would be 0 to 0, index 0 to index 0. We can scroll up a bit and you can see over here I had 1, 2, 3, 4, 5, 7, 6, 2, 5, and 3, right? This was my values. Now when I moved to the right over here, what was my range? It was 7, 6, 2, 5, 3, but with the 2 and 3 gone. So it's 7, 6, and 5. So do you see how even this is a range from indices 0 to 2? And we did that again. We moved down to the left child in this case, and we cancelled out the 7. And now we're left with 6 and 5, and again we have a range. And again we went down and we have a range. So that was what I was saying. I was saying that at each and every level you go down, you're going to have a range. And it's very important that we have a range, by the way, because the prefix, something I said before, kind of relies on the fact that you're always querying a range, right? Okay, so did you guys understand what the range statement means now? Okay, a bit confusing. Okay, that's fine. I will just repeat again. That's completely fine. Okay, so Advik, what does this blue thing I've drawn over here mean? Or what does the query in question mean in the first place? Uh, Also, I can't see chat right now, so I would appreciate if you could speak. Because otherwise, I'll have to like continuously, like if you're comfortable with it.
Yeah, it's fine.
Okay. So, what does the blue range over here represent? This one over here.
Uh, the query, the range and indices, like what you said.
Exactly. So, I'm saying I want to find the third element in these indices, right?
Yeah,
So, now what actually matters? The thing that matters is the values in the indices, right?
yeah,
So now what I'm doing is I'm doing a binary search and I'm saying, okay, I've determined that for sure the value we want is not less than or equal to 4. So let's cancel out all of the numbers that are less than or equal to 4. And then we're left with this smaller range that's 7, 6, and 5. So now what I mean to say is that when I go to the right child, because when I determine that it's greater than 4, that means I go to the right child. The 7, 6, 5, if you notice, it's in a contiguous range over here, right?
But if you cancel out 2 and 3, and you know that 2 and 3 are the for first and second smallest kth value, how are you keeping track of that? The canceling values.
Okay, good question. So actually, maybe I didn't elaborate on this much, but k is equal to 3 over here, right? And I removed two smaller values. So now I'm saying k is equal to 1. We need to find the first smallest value in this smaller range because, like you said, we removed two of them. So you are keeping track of that. Don't worry. Was that a bit unclear, or do you still have questions regarding that part? Because I would understand if you do. Or does it make sense?
You can keep on going. I think I will. I have a bit of understanding here.
Okay.
One sec. 1765. Do you mean they are continuous in the original array or continuous now?
They're contiguous now. They're not contiguous in the original array, right? Because there's two in between, there's three in between. But we never wanted them to be contiguous in the original array because that wasn't our predicate before, right? Before we didn't get rid of any values. We had this whole ass array. Like we had the entire array. We hadn't got rid of anything yet. But now what are we doing with the binary search? We're trying to get rid of some values, right? So the first thing we're gonna do is we're gonna try to get rid of values, all values that are less than or equal to 4 in our range. So that's 2 and 3. Okay, when we get rid of 2 and 3, we're going to the right, and I'm basically saying that the remaining elements will always form a range because, like, think about it. You have this range, and you can imagine like removing the values like with your hand or like canceling them out, and then pushing all of the remaining values like closer together to form a normal array, right? And then you can realize that, oh, if I have a range in the original array, it's just going to be like a slightly smaller range in the array with the elements removed.
Yeah, but wouldn't it be better if we store the indices in the original array because the LRR we're given depends on that.
Store the indices as in.
Like if I have five in the original array was at fourth index, but like third in the part we're considering zero based. But now it's
Yes,
two.
yes.
But now it's two.
Yeah, yeah. So that you actually do store LNR of the range. You definitely store that. Yeah, you have to store that. In fact. So what I was saying is, you now know how to do it, or I hope you do at least. Like if I give you this diagram and I tell you simulate how a wavelet tree would answer a query, you would correctly be able to cancel 2 and 3. You would correctly be able to identify that this 765 from indices 0 to 2 in the smaller array is the subrange of 1 to 5 in the bigger array, right? At least I hope so, right?
Yeah, I got that part, but you said that we'll form a binary array consisting with if AI is in the less than equal to the predicate or not, and then you just make a prefix of that array. So for
Yeah.
that, you have to know the indices, right? So you'll do it for the smaller array first, right?
Okay, wait. So the thing is, the that array which I said the prefix sum array is relative to the indices of the smaller array. It's operating on the indices of the smaller array, not on the bigger array.
Oh wait, I got it. I got it.
Okay, great, great. So now everything that's we have done so far just goes down to this singular question: how do we efficiently go from knowing that this is 1 to 5 to knowing that this is 0 to 2? So, just give me a second. I actually have like the perfect binary tree to figure this out. Not binary tree. What am I saying? Perfect array to figure this out. And I'll just draw that on the screen here right now. I don't know what happened to my cursor. Yeah, here it is. Let me just try to find it. Okay. Goodness, my iPad is lagging so much. This is like actually not even funny anymore. Okay. So this is the wavelet tree I've drawn. Okay. Now I first of all want to point out that the prefix something I said before. Let's just do that. Let me like write that. I don't know over here on the side. I'll just make the prefix sum array for the predicate for 50. Okay. So now if I look at 20 over here, let's look at what its corresponding thing in the prefix sum is. It's 1. So my first question to you guys is, do you see how the corresponding thing for an element in its prefix sum is going to be its 1 based index in the left array? If this doesn't make sense to you, think about it as the prefix sum is basically counting how many elements go to the left array, right? The amount of elements less than or equal to x are the elements that go to the left array naturally, right? So this is counting how many elements go to the left array until this point. So until 20, how many elements have gone to the left array? The answer is 1. This must mean that the index of 20 is 1 in 1 based indexing, right? So this is the first thing. So this actually looks really nice for us, right? Because oh my god, like that just worked out so well. We literally just went here and map left was this. So that's our first transition state in a way. But we need to make sure we subtract 1 just because we are dealing with zero based indexing, right? And this was one based indexing. Now, what would it be for the right one? Uh, the best way to understand this stuff is to actually just take an example. Let's not take that example. Let's take something like this, maybe. Just real quick, are you guys understanding what I'm trying to do? Yeah. Okay. Okay, great. So now my question is, if I can present. Yeah, my question is I figure out that L is equal to L goes transitions to prefix L minus 1. My question is now what does R go to if I'm considering the left part? What does R go to? Anyone with an answer?
I'm not able to understand the question.
Okay, okay. I'll repeat the question. Basically, did you understand what I did before? The run through I was doing with that tree, where I was
Ah,
going through how you do a single query, right? You understood that?
yes, yes.
So now, what was the part I didn't cover? I covered like pretty much everything in Wavelet trees, but there was one thing I left out, right? What was the part I left out?
The range query.
The range that you go to as like the child goes to. Yeah, I left that part out. So now this is what I'm asking you guys. How do you fill in that missing part? So now I'm just saying I have a range in the parent array. How do I go to the child array part of it? That's my question. Like how do I how like if this range is 89 to 98, right? I want to say I want to go to the left child. I'm saying, oh, this includes 20 and 12, so this will be the next corresponding range. Like, do you understand?
So we can just see the in which the
Sorry, your voice kind of lagged out. Could you please repeat?
you want us to tell us what how to go to R or the right child.
We need both. We need an algorithm to go from the current node to the left child and the current node to the right child. We need both.
We can just see on which prefix if the current prefix some changed or not.
Okay, as in?
Uh, wait.
Oh, don't worry. It's not as easy as it looks. Like the problem looks very simple at first, when I explain it, but then it's like,
Please check the chat once Advik is typing something.
oh, I will check. Yes. Left L is equal to PL minus one. R is equal to P mid. Right L is equal to P mid plus one. Right. Okay, so I'm pretty sure mid is not involved. So we actually might be mistaken. Um, just want to check if I'm not remembering like severely wrong or something. Just give me a sec. But no, I'm pretty sure. Yeah. Okay. Hmm. So firstly, I'm going to do something that will make this question a lot easier. And that is, instead of considering our range to be L to R, let's consider our range to be L to R with R being exclusive. Now, the reason this makes this easier is something you will see retrospectively. For now, I will just say, take my word on it, it makes it easier. So, first of all, do you guys understand what this means? Basically, this means, let's just go back to that original question, the one which we claimed we were going to solve, which is over here, yes. So you can see what the query is. It's L, R, and K. Print this in the range AL to AR minus 1. Do you notice how it's not AL to AR and it's AR minus 1 over here? Basically, this means it's inclusive of the left element, but it's exclusive of the right element. So it doesn't include R. This is basically uh, equivalent to this. But I'm saying taking our indices as half closed would make it easier. I'm claiming that would make it easier. It doesn't seem to, but it will make your code clean. You know what? Okay, fine. We've taken so many values, I forgot the original question. Don't worry, it's almost over. This is the last part, and after this, we can go to the original question. Like, this is the only thing remaining. Like, let's say like 80-90% of it is over, so. Okay, see, the thing is, you want to avoid using binary search. You want to go for transitions. Just because you want the time complexity to be log n and not log square n. Yeah. So that would be log per level and there are log levels, so log square. Yeah. But we don't want that. We want a way to answer every query. It will pass. I'm not saying it won't, but there's a better way. The thing is, you can leverage the information you have stored in that prefix array itself to do these transitions really fast. The key insight over here is to realize. Did you guys hear what I said about the prefix something? Like if I have wait, um, I was saying that if I have this 20 over here corresponds to a 1 over here, right? This means that the 1 based index of 20 is equal to 1. This 12 over here, it corresponds to a 2. So that means the 1 base index of 12 is equal to 2. But then you'll say, oh, but this 98 corresponds to a 2 as well. Does that mean the 1 base index of 98 is also 2? But so this logic only works if the element actually goes to the left. But if it does go to the left, then we can do this. You know, for simplicity's sake, I am just going to uh, Only first occurrence of I in the prefix array counts. Okay, there's a way you can do it without using mid at all. Okay, you know what? Since we are kind of running out of time and I want to cover the original problem as well, what I'm going to do is there's going to be a written resource at the end. Yeah, go on, go on. There's going to be a written resource I'm going to release after this, and if you guys are really interested, I'll show you like a proper motivation for this. For now, I can give you rough motivation because even that's pretty powerful. And honestly, I feel like deriving this yourself would be better for you guys as well to understand it. But I'll just tell you right now what it is. So we're going to assume one-based indexing. In that case, for the left, remember we're assuming one-based indexing and half open intervals. L is going to map to prefix of L. Now what about right? Oh, sorry, not R. I should have started with L. Okay, so let's start with these. Do these first things make sense to you? Let's not talk about like plus or minus one. Let's talk about the general concept behind it. Do these make sense to you guys? Why this would be L and this would be R? That like I'm pretty sure you guys can understand that, right? At least. So like I was saying, the actual thing corresponds to the one-based index of this, right? So the one-based index of 20 is going to be this in the left, and the one-based index of whatever the next element is going to be that. This works well because even if we are beyond it, like let's say we're at 98, we anyway don't have to include it, so we're just going to automatically kind of go back to this. So does it like kind of make sense at least? Like I just want to give you guys the intuition about it. Okay. Yeah. So like ignore the plus and minus ones. Just look at like it from like a conceptual point of view. Like you can see how it would be some prefix of L plus one, maybe prefix of L plus one minus one, something like that, right? But it's going to be prefix of L. The next part um, is if you're going to the right child, then L is equal to L minus prefix of L. Because what do we have to do basically? We need to go and we need to subtract off all of the values that went to the left child. So L minus prefix of L is saying that okay, till L there are L values, except the ones that went to the right, went to the left child. So I'm removing these, and now these are the remaining. Okay, I shouldn't have removed the ones. I should have removed the zeros. Oh no, wait, I do remove the ones. They're the ones that go to the left child, and these are the ones that go to the right child, right? So it's L total values minus the ones that go to the left child. That's the index of the left in the right child. If you're going to the right child, exact same logic for R. And then K is equal to K minus R minus L. This looks a little confusing, but it's actually not confusing because you need to just realize what R minus L is. What is R minus L as a quantity equal to? It's equal to the number of total values in a range which belong to the left child, right? If you remember the prefix r minus prefix l minus 1, so in this case, because we're using these kind of intervals and our prefix is 1 based index, prefix r minus prefix l will give you the number of values in the range that are going to the left child. So in the examples we saw, we were just subtracting this out. So k becomes k minus this. So I'm repeating again, this is not meant to be like a formal proof or anything. This is just meant to be intuition for the transitions. And this is the simplest possible state of the transitions. And if you code it using one base indexing and a half open intervals, these will be the exact transitions. But I don't want to like prove that to you. I just want to show you why it's plausible, why it makes sense. And I hope I convinced you guys of that, at least. Oh, I'm sorry if my perceived confusing things were actually easy and the other way around. But prefix L have people in range less than or equal to L. Less than or equal to the predicate, not L. Less than or equal to M, that is, yeah. Repeat which part? That's the solution, yeah. No, less than or equal to people from 1 to L who are less than predicate. Less than or equal to predicate. But yeah, you can make it less than predicate, but then your transitions would change and it would get really messy. Removing things in actual indexing. Okay, I'll repeat that part once again. Okay, wait, I'll just answer Alok's question first. How does L minus prefix of L work? L is the total number of. So, by the way, we are assuming one based indexing now, okay? So, our first index is 1, not 0. So, in this case, because that's the cases under which these like elegant transitions work. Uh, so, this L over here, basically now with one base indexing, this means the total number of values, right? Up till L. Now, when we subtract out prefix of L, that means the total number of values that went to the left child. So what is remaining? Total values minus values went to the left child is equal to values went to the right child. Okay, yeah. L should be increased as in like you're saying L plus 1 or something. Okay, see the thing is prefix of L is the values that went to the left child. It's all everything should have to be decreased if you think about it. Because you're removing values in both cases, right? Even for the left child, you're removing the values greater, so the overall indices will go down. Yeah, that's what I'm explaining. So L right now is the total number of elements up to L, right? Prefix of L is the number of elements that went to the left child, right? Like the elements from 1 to L that went to the left child is prefix of L, the number of elements. So now if I subtract that from L, I'm going to be left with the remaining elements, which where did they go? They went to the right child, right? So L minus prefix of L is the number of elements that went to the right child from 1 to L. And that's going to be the index of L. Yes, they do. That's stored in prefix of L. So just imagine this total is equal to left plus right. Right? What's the total equal to? L is the total. What's the left equal to? Prefix of L. Do you agree with the fact that left is equal to prefix of L? I'll just write this for now. You agree with this, right? Or okay. So basically I'm saying I'm considering all of the elements from okay, actually better than this, I'll just explain that one based indexing thing again. Just let me present my screen. So look at this over here, this array, less than or equal to 50, greater than 50. Okay. Now look at this array which I've made. The ones correspond to the elements that are less than or equal to 50. I prefix sum the array and I get this array. Now, if I look at the index of 20, or sorry, if I go to the prefix of 20, that's going to be 1. This corresponds to the fact that in the left array, 20 takes up the index 1. That's what I'm saying. And if I look at 12 over here, it's equal to 2. That corresponds to the fact that 12 here takes the index 2. So that's the main thing which you need to notice about the prefix array, the map left thing, is that prefix of I is equal to the index of the thing in the left array, or equivalently, it's equal to the count of the number of elements so far that have gone to the left array. Now, if this is clear, then what I'm saying is that how did we find the index of the left of like something? How did we find it translated? What we did is we found the count of the number of elements that went to that part, right? Because we're using one base indexing, both of the statements are equivalent, right? Okay. How many of you guys understood the what do you say, the prefix idea I just explained? Just forget everything else. Just that idea. How many people understood that? L is the left endpoint. Oh, okay. So L is the left endpoint of our range. R is the right endpoint of our range. Left refers to the left array, and right refers to the right array. Yeah, it is L to R minus 1, but I'm taking the range as this because I claim it makes it a lot easier, the transitions to right. Yeah, possibly true. Yeah, I don't know what I was thinking when I said short Wavelet trees lecture, but that's fine. Did you understand the idea of the prefix sum mapping to the actual index? Uh, Advik, did you understand that idea as well? Didn't get prefix L. Okay, you know what? Forget prefix L. Just think of it as prefix I. Let's say you have an index I. I am claiming that prefix I is going to be. Yeah, okay, sure. Yeah, I'll try my best to wrap it up before 11. I'll just try to explain this part first. Yeah, so I was saying the index of element 20 is going to be 1 over here, right? In the left array. And prefix of 20 is also equal to 1. The index of element 12 is going to be 2 in the left array. And prefix of 12 is also equal to 2. That's literally it. That's what the prefix I idea is. Um, that's a good question. Now I'm saying that if I want to convert my left and right to go to the left tree, of course I just do left is equal to prefix L, R is equal to prefix R. But now, okay, now do you agree that total is equal to left plus right? I mean, we're just going to do the same thing again. So I is equal to left plus right. I is the number of total elements till that point, right? Now, what is left equal to? Left is just equal to prefix of I, as I just explained. That's the number of things that go to left. I gave you the dry run as well, right? That's the same idea. You don't get the part how I is equal to prefix of I. Yeah, so it kind of only applies to it kind of only applies to indices where they are actually part of the left, so they are less than or equal to mid. But it turns out that you don't even need to care about this when you consider. Okay, wait. So I'll just write the exact same example here. I'll just make you do it now, so maybe that will. Uh, can you tell me what the predicate, or sorry, the 0 1 array would be? The array for the predicate. Just write it in chat. Yeah, that you directly prefix summed it, but yeah, that's fine. 0 0 1 2 2 is correct. Yeah. Now, can you tell me what prefix of remember one base indexing? Can you tell me what prefix of 3 is equal to? What is original array of 3 equal to? So I'm claiming that the 20 element number 20 or not element number 20 element 20 takes the index 1 when it goes to the left child. Oh, you got that part. Okay, wait. Then which part did you not get? Left is equal to prefix of left, not prefix of I. Because you agree that I is equal to prefix of I, right? Okay, you know what? Let's change the range to start comma end. Yeah, Hardin is right. I is equal to prefix I for all I, so put as L and I. Exactly. That's exactly what I mean. Yes. Now for the right child. Yeah, or I can explain it after class too, because I think some people need to sleep as well. Uh, for the right child, I've coded this, so I'm pretty sure I'm right. So for the right child, it's just going to be I is equal to I minus prefix of I for all I, like how Hardin said. But now, so like you guys don't need to understand the exact transitions. What I hope you guys took away from this is the concept of a wavelet tree and how that works. Because if you guys got that as well, then I'm gonna take it as you guys know wavelet trees. So I'll take that as a win, and then you guys can figure this out yourselves later because these are just implementation details to be completely honest. Okay. Now, do you guys want to see how you'd code this, or I can just wrap it up? It's up to you. How many people here would be interested in seeing me implement this? Okay. Okay. Great. Oh, okay. No, no. It's like a function. F of I is equal to I minus prefix I. That would be more accurate to say. Okay, yeah, I'll code this fast just so like some people who need to sleep and stuff can do that. I'll put my font size like to this. So let's just ignore the main function for now. Let's start with class usage. Maybe I should have held this lecture in two parts. I don't know. That may have been a decent idea. Yeah, this is also true. But some people like to see it implemented to clear everything out. So now I'm going to implement this in a very unique way, which will it will make sense once I do it. What I'm doing over here, I'm taking in min and max. I'm setting these min and maxes to this, and I'm making iterators L and R. Okay. Now what I'm going to basically do, I'm going to populate map left. So first I'm going to do map left, or I can actually, like I said, I was doing one based indexing. So by that, uh, by that claim, I'll set map left 0 to 0. Do you guys understand what this part is doing? Oh, I can explain that later, honestly. But you can do it. So, iterator L, iterator R. Map left is the array we discussed. This is the prefix summary, okay? We're setting it to 0 because we're using one base indexing. Then this is just some basic index math. Let me just see what this is going to be. At max, this is going to be R minus 1. So the minus 1 and plus 1 goes away. Anyhow, R minus L, yeah, the size is big enough. Yeah. So it minus L plus 1 is going to be the next value over here is going to be the previous value plus whether the predicate is true or not. If the predicate is true, this is 1, otherwise it's 0. So this is the exact same prefix sum idea we discussed before. Oh yeah, right, I need pointers. My bad. So you don't have to code this with pointers actually, but it's the easiest way to code it. So I'm just going to code it with pointers for now. Then what we're going to do is if min is equal to max, then we can just return because we don't need to do the divide and conquer otherwise. If min is equal to max, otherwise we're going to do the divide and conquer. We're going to say we already calculated m is equal to min plus max by 2. We're going to run this function called stable partition. Uh, so this function takes in the first and the last points, so that's L and our predicate function, which basically is going to be that our value should be less than or equal to m. And this is going to return the first point where this is not true. That means we need to now do left is equal to new wavelet tree of L it. Of course, I need to pass in min m lit and right is equal to new wavelet tree from m plus 1 to max itr. I feel like I'm forgetting something, right? The destructor. Okay, Okay, this is the construction. This is the divide and conquer construction we discussed before. Also, maybe it's possible that my implementation is like a bit complicated for you guys to understand. If that's the case, then what I want you guys to take away from this is number one, how I'm using stable partition, because that's important, right? You can code this manually, but you should use stable partition. I really recommend it. Secondly, what this iterator business is, why I'm passing iterators to constructors, how I'm iterating through it, and this syntax, the L, IT, and ITR over here should make sense. So I just want you guys to take away as much as you can from this, and I want you to see like slight resemblances to the logic we discussed earlier as well. And if you want, I can send this code later on, or I can just send you my AC implementation as well. No, this is the construction, yeah. And then there's yeah, it's pretty short to code actually. Now the kth element part. What we're going to do is if min is equal to max, then we don't need to binary search anymore, so we just return min, right? Otherwise, what we're going to do is we're going to calculate n time is equal to min plus max by 2. We're going to say, how do we see this? If we have enough things in the left, so that's left map left of r minus left map left of L is greater than or equal to k, then we need to return the kth element, or sorry, left kth element with map left of L, map left of R and K. This is the index translation idea. This is where I think most of you guys were confused. So I really think you should sit down, get out some paper, draw like a wavelet tree yourself, and look at how the indices change when you go to the left child and when you go to the right child. Now I claim it changes like this. You may not believe me, which is why I want you to try it out yourself. But since I need to wrap up this lecture soon, I had to move on, right? And otherwise, we return the same thing for the right child, but it's L minus map left of L, R minus map left of R, and K minus L. Sorry, K minus this quantity. So in fact, I can make a variable for this quantity. Maybe I got left count is equal to this, and then yeah, this is the whole wavelet tree. This is the implementation. It's fully done. So yeah, as you can see, it's like really short, right? So one more thing I want to point out, it would be longer if I didn't use stable partition. If I didn't do this array thingy where I made my constructor this really specific, complicated looking thing, it would be longer. So there's like I've used like STL over here and stuff, right? So maybe that would be an explanation as to why it's this short. But yeah, that's the entire implementation. So yeah, Secretary has shorter implementation. I feel like both are equally cool. So the thing about me is I'm like a real Secretary like fan. So I wouldn't necessarily say this is better than Secretaries because I just love Secretaries so much. But Wavelet trees, I don't know why they're not taught because they're like also a really cool data structure. Also, Nihal, that's fine if you can't understand the code. I hope you at least grasp the high level idea of what the code is trying to do. Um, okay, yeah. I did not send you guys the problem, or did I send the problem? Where is it? Yeah. Try your best to solve this problem using the concepts we discussed. Okay, I see. Yeah, everyone here, try solving this problem. It will teach you a lot. Maybe you don't have to do it immediately after this lecture, maybe tomorrow. I don't know, whenever you get time, you should sit down and try doing this problem just to like consolidate what you have learned in the lecture. But yeah, other than that, I'm pretty much done. My work here is done. If you guys have questions about anything, you can ask me on Discord and I'll try my best to reply to all of them. I hope the lecture was interesting. Fun, maybe. I don't know if you guys would like to call it fun or not, but I hope it was. I hope you guys understood most of what I was talking about as well. And yeah, that's pretty much it from me. Thank you.